OK, so now we get to move on to even more complicated processors. In-order issue, or excuse me, in-order front end, in-order issue, out-of-order write back, and in-order commit. OK, so this is going to solve some problems that we have. The biggest problem it's going to solve is it's going to solve a problem of precise exceptions. We can now have exceptions sort of all the way at the end because we're committing data in order. So let's take a look. That should probably have a line there. You can scribble that in on your own drawings. OK, so let's take a look at some other structures we've added to this diagram to make life a little bit more interesting. OK, the front end looks pretty much the same. We split the load and the store apart into two separate pipes here, a load pipe and a store pipe. And the store pipe is shorter because it just has to basically do a store, we'll say. Maybe it's 2 stages. Doesn't matter that much. It's not that material in this drawing. But something interesting to look at here is we added a bunch of extra boxes over here on the right side of this foil. So let's define these things. So we had our architectural register file, which is our committed state to the processor. And we added a second register file, typically called a physical register file, or PRF. Sometimes people call this a future file. And you'll see that in the literature. There's some papers published about future files. And the reason it's called a future file is it's basically executing speculatively in the future. The values in here have not been committed to the processor. They can be thrown out. If you take an exception, if a branch happens, for a variety of reasons, these are speculative. You're not guaranteed to actually have to keep those. The architectural register file, though, is committed state. OK, we added 2 other structures here, something we call a ROB, or a reorder buffer. And we added a finished store buffer. So let's talk about the reorder buffer first. So in this pipeline, we actually want instructions to basically execute and write the physical register file out of order. Because this is an out-of-order processor. We'd like that to happen. We're basically making the execution and the write back out of order. But we want the commit to be in order. So we need some structure that is going to guarantee that the write to the architectural register file happens in order. And that's what the ROB is going to do. So what it's going to keep is it's going to keep completed instructions and that could come in out of order and are going to leave in order. So things come into this out of order, and they go out of it in order. And this is a reordering structure. It's typically a table that is sort of written. Well, we'll talk about that in a second. It's written in different places in the pipe for a couple different reasons. But you typically want to keep track of the instructions in order somehow. And then when you go to pull out of the reorder buffer, you want to pull in order out of it. But the writes and the tracking of the information that happens to it can be out of order. And the other thing here is this finished store buffer. The reason we have this finished store buffer is if we have a store operation, we don't want to have the commit point like here so early in the pipe. Because once you store to main memory, it's really hard to go get that back, possibly even impossible. It probably is impossible. You wrote to the main, if you had the old value and you overwrite it with the new value, the old value is forever gone in your main memory. You can't get it back. So the solution to that is instead of doing the store here, you have the store happen later in the pipe, and you just sort of remember what you're supposed to do, the address and the data that's supposed to be happening. And for anybody who cares, that store has happened if it hits this future store buffer. So you probably need to have your loads check that future store buffer with higher priority than your cache, because there could be a store living in that location. OK, so that's the sort of structures here. Let's talk about where things get read and written. This one's really interesting. Our architectural register file isn't read anywhere. What's up with that? Well, we're going to use the physical register file for all the intermediate values in our pipeline. And the architectural register file is only there if we take some sort of, let's say, branch or interrupt. And that's the only time we actually need to go take this information, and we probably want to dump it into the physical register file or dump it into the future file when an interrupt happens or when a branch mispredict happens. But otherwise, it doesn't have to be read. Scoreboard is the same as usual. Read and write in your register fetch stage, written at the write back stage. And that's no longer tracking architectural register file registers. It's now tracking physical register file registers. Reorder buffer. This one has a whole bunch of different places it gets read and written. Primarily, what's going to happen is when the instruction is issued, so it goes from the decode stage to the issue stage, that's going to allocate a location in the reorder buffer for the entry in the reorder buffer. And then at the end of the pipe, once the value completes, we have to change some state information in the reorder buffer saying, oh, that output register for a particular instruction is now ready. And then once we actually go to do the commit, we have to basically clean that instruction out of the reorder buffer. The future store buffer is written just sort of at the end of the pipe here and cleaned when the actually post to main memory. It's a little hard to draw this, but that information, somehow through the memory system, if you have a load that reads from that, we'll probably read it either in L0 or L1 in a sort of a bypassing mode, if you will. It'll go check that structure. We'll talk more about that next class. OK, so here is sort of a basic reorder buffer. If you go look in some books, they have a lot more data stored in a reorder buffer. But this is kind of the minimal reorder buffer you need for an out-of-order pipe. And this reorder buffer is used to keep track of in-order committing of instructions, but things will be put into it out of order. So just let's first talk about the sort of information in here. We keep track of state. So what do we mean by state? So this is the state of an instruction. So each one of these entries here is a different in-flight instruction in the pipeline. And we're actually going to store in order into the reorder buffer. And we're going to keep it sort of as a queue. So this picture here, this state is, we'll say dash dash means free, and P means pending, and F means finished. Probably should not have chose two F words there. That's a little confusing. But the newest instruction is if we have a new instruction execute, it's going to end up here in this entry. And when an instruction commits or retires, it's going to remove this entry, the bottom entry. So we basically have a sort of circular buffer running around. There's a head and a tail pointer sort of chasing each other in this data structure. So tail, head. What's interesting about this, and why this is cool, is because let's take a look at this instruction right here. This instruction has an F, which means it's finished, that it's not pending in the pipe. It's hit the reorder buffer. The data is stored in the physical register file. But instructions that are older than it, which would be these two instructions, are still pending in the pipe. So let's say these are two multiplies, and this is an add. So this add is basically already done. These two instructions, which are these long latency instructions, are still pending in the pipe. In this cycle, we cannot commit anything. So we only commit instructions when the oldest instruction becomes finished. And that's when we can commit and remove something from the reorder buffer. Some other things we need to keep track of here. We have a bit here, S, for speculative. So what this means is if you have something like a branch, you mark instructions that are newer than the branch with a speculative bit. So what this is saying is if that branch mispredicts, it just gives you a convenient place to go find all the dependent instructions on it to go flush and kill. So if you have, let's say, one branch is allowed in the pipe at a time, and the branch mispredicts, what you can do is basically look for all the entries in here that have ones and just invalidate them ad hoc and just flush the entire pipe. You don't have to worry about there being some value you need to worry about. So it's just a convenient way to figure out which instruction is speculative, and if the branch is mispredicted, what you have to kill. Stores. We'll be talking about this in a few more slides later, but store bit, what it's really going to do is this is going to say, if this instruction is a store, it knows that we need to do something else with it. We need to do something with the future store buffer when it gets to the end of the pipe. It's sort of a convenient place to put it. And then here's the actual business, the business part of the reorder buffer. V, which says that the instruction actually writes a register. And then finally, once the instruction goes all the way to the end of the pipe, it is going to fill in a location in here, which is the physical register file entry that is the destination of that value. So this basically allows the pipeline to know where to go find the actual value. We don't actually store the actual values in here. We just store a pointer into the physical register file because it's fewer bits. And this can tell us, oh, well, go look, let's say, when this instruction here, which is already finished, is ready to go retire, or it's ready to go commit, go look in physical register file number 7 or something like that, and it goes and pulls that value out from there. So a good discussion of this is in the Shen Lepaste book that is sort of supplemental material for this class. OK, so let's talk about the does anyone actually have questions first before we move on? Because reorder buffer is a key data structure here, and it's a complicated one. OK, great. Next structure we added was the finished store buffer. And this could actually be multiple entries, but for this pipe, let's just say there's only one. So we're only allowed to have one store pending in this pipeline, because it makes life a little bit easier. Things you sort of need to actually have here is you need to have both the address and the data, whether it's valid, probably the opcode. Maybe the opcode will tell you if it's store byte, store word, sort of data width types of things. And that's most of what I wanted to say here. This is what I was saying before, is if you allow multiple loads and stores in the pipe at the same time, you're going to have to bypass from the finished store buffer to the loads. And possibly even stores if it has to write combine. So if you sort of store to different parts of a word, you may even have to bypass that, depending on how your pipe works. Or you can assume that there's only one memory instruction valid in the pipe at a time. You can have one of these entries, and no loads can happen while a store happens. That's not very good performance. People probably would never actually build that, but that's something to think about. OK, so now we get some more pipeline diagrams. I run those pipeline diagrams. And we're going to see how this is different and what happens in the reorder buffer. First thing I wanted to say here is this little r that you see show up in these diagrams. That means that we've written the reorder buffer, but we're not ready to commit. So from here to there, we basically have this add has written the reorder buffer, and we're waiting for it to commit at the end of the pipe. But we can only commit in order. So you can sort of see these C's are all lined up in time. So we're only able to commit from left to right, and we can't reorder one of those C's relative to another C. Let's see, what did I want to say here? That was the main thing. The dependencies are the same. It's the same code we've looked at before. That's what I wanted to say. Which one is that? Yes, it's this one. OK, so here we have this add writes register 12 right there. This add goes and reads register 12. So we have a read after a write happening. What's interesting here is this read after write that's happening. The write happens there. The read happens, let's say, here. That data is not in a bypass anywhere, or it's not in the forwarding logic of the processor. That value is actually in the physical register file. So this is kind of showing an example here that data, when you're doing the bypass, can come from bypass network locations. It can come from the physical register file. And those are sort of the two places it can come from. But you can, everything else actually in here, surprisingly, is basically coming from bypass, except for that one location. So bypasses end up being really important. But you can have data coming from the physical register file. So could the C be here? Could this C move over one? So it's commit in order. And we can only commit one thing at a time in this basic pipe. More complex pipes, we're going to allow multiple commits at the same time. When we start to mix superscalars with out of order, at the end of today's talk, we're going to be able to think about trying to commit multiple things at the same time. But we can't really do out of order, so this has to be monotonically going that way. Brief example here. This is kind of fun. This is trying to show different entries in the reorder buffer and when those things get allocated. And largely what's going to happen is for a destination, so let's say instruction 0 here allocates the reorder buffer, and R1 becomes active. And it's a long latency. It's a multiply. It doesn't show up. The circles here mean that the instruction is finished. It's gone to the end of the pipe, and it's ready to go. You could have other things, like this is an add that happens to register 11. It allocates, it finishes early, but it doesn't commit till late. So it has to stay in the reorder buffer. So it takes up space in the reorder buffer. And you can sort of see other examples of that. These adds here finish relatively quickly, but they have to wait to commit in order. And they're basically dependent on this instruction here committing before they can go commit. So it's a nice little structure that can track all of those things. OK, let's look at commit points and if exceptions occur. We're going to have the same example we had before. The mall here is going along, and it write-backs to the physical register file. Now you're going to say, whoa, it wrote the register file. How can it take an exception at this point? I thought if it took exception, it wasn't supposed to write the register file. But we have two register files. So it writes the speculative state register file, or the future file, or the physical register file. And this slash here means we don't actually commit that instruction. So the commit doesn't happen. Now we get to go look at sort of other in-flight instructions to see what's going on here. Can these other in-flight instructions potentially write information out of order, and where can our commit point be? Well, here's this add that before in the previous example wrote to the register file, and now it writes to the physical register file, but does not write the architectural register file. Instead, it enters the reorder buffer here, denoted by the little r, and just sits there until it actually gets a chance to commit in order. But that doesn't get a chance to commit, because a previous instruction kills it, and because it takes an exception, and kills everything. And then you can go and start some new instruction here, let's say, that is the exception handler, and fetch that out here. One interesting thing about this example, actually, that I wanted to say is sort of in this transition, lots of stuff, lots of state has to change in the machine. You've taken an exception. The architectural register file is correct. The physical register file potentially has many incorrect information, or many incorrect values in it. So on this transition, what's really going to happen is you're going to copy all of the state of the architectural register file, all registers, over on top of the physical register file. So you've basically rolled back all of your speculative state in the machine in one fell swoop. Obviously, that can maybe be a little bit expensive, but you don't take interrupts that often. You do take branches relatively often. We'll talk about that in a second. But what's nice, that's logically what's happening. Sometimes people will actually commingle the architectural register file and the physical register file, and they just sort of keep pointers to different pieces of information. So you don't actually have to sort of roll back information. You just sort of change the pointers. But for right now, let's model it as two completely separate register files where you copy all the state from the architectural register file to the physical register file on some form of rollback on an exception or a branch. Branches. So how do we make the branch latency better? Or what do we do on a branch, first of all? So sort of ignore these bottom examples here. This is a different code sequence that we've been looking at. This is not the multiply, add code sequence. Instead, this is a branch. So we have a branch. The branch commits. We know the branch is good. But these instructions here are the fall-through case for the branch. This instruction here is the target for the branch. So we need to squash all of these instructions in the reorder buffer. Conveniently, we have a bit in the reorder buffer that says all of the things that were dependent on the branch, if the branch is misspeculated, just remove them from the reorder buffer and basically throw everything out of our reorder, or throw those entries out of the reorder buffer, invalidate them in the reorder buffer. What gets a little interesting here is when do we start to execute the target? Well, let's say we compute the branch information here in the execute stage, and we can sort of redirect the fetch stage. That's OK. But this squash is a little bit odd. Because what this really says, from a pipeline perspective, is that you have to invalidate multiple entries in the reorder buffer in one cycle. And this, to some extent, is a structural hazard on the reorder buffer. You might need many ports into that reorder buffer, or you need to at least keep the valid bits in some other extremely highly ported structure. You could think about doing something even more interesting, where you kill instructions early. So the difference between this picture and this picture is once we compute and figure out that the branch is taken, we just instantaneously squash all these instructions, and we change the reorder buffer. Or we write to the reorder buffer, killing all the speculative instructions. Now, if you note, this doesn't actually help performance in this case. Places where this can help performance is if you have an out-of-order processor that's a superscalar processor. You could think they could try to sort of put other instructions in these locations in the pipe, or try to restart earlier, or have other things go on in the pipe, and you're just using less resources in the pipe. So this is going to be the highest performance case. This is sort of going to be medium performance. Low performance, you can have a way that you don't actually have to add extra ports to your reorder buffer. And the way you can do that is you let the in-flight instructions that are dead continue going down the pipe until they get to the commit stage, and only then do you clean them out of the pipe. And you clean it out of the reorder buffer. So you sort of are waiting for these speculative instructions to reach the commit stage and then squash them there. In this example, the performance of all three of these are the same. But I will say this is going to be the lowest performance if you have a more complicated code sequence, because you are basically using up a lot of pipeline resources. You're using entries in the reorder buffer. You're using locations in the pipes that you could try to reuse for something else. OK, so as we said, we sort of have these three different cases in increasing complexity. But you get some performance. In decreasing complexity. but increasing performance. So I think one thing that definitely comes up, and this is probably going to make this multi-ported issue come up, is if you start to have multiple branches in the pipe at the same time, then the simple case of just moving the tail pointer is not really going to work, because you might mispredict one of the branches but not the other branch. That's going to mess you up a little bit. OK, so let's keep moving on here. Avoiding stalls due to store misses. OK, so you got a store in the pipe. It takes a cache miss, and now it's clogging up the commit point of the processor. Because depending on how you want to look at this, maybe you don't want to commit until that store has actually reached main memory, because that's what you're going to call commit for that store. So you can't necessarily pull it out of the future store buffer, because it's not able to actually sort of commit. You try to pull it out of the future store buffer and write it to main memory, or you write to your cache. It misses in your cache and takes a couple extra cycles. So we'll see like this. Here's a store word, and let's say it takes a few extra cycles here, 3 extra cycles stalling to actually go and write the level 2 cache, we'll say, or pull in the data from the level 2 cache into the L1 cache and merge there. So there's a way to solve that. And what's bad about this is because we're doing in-order commit, it pushes out the rest of these instructions later. And that's kind of bad. So what you could think about doing is adding an extra stage in the pipe and just allowing the store to miss and basically moving it past the commit stage, saying this store has committed. You just sort of mark it down and say, well, it's committed. I don't have to worry about this anymore. And you basically can decouple the end of the pipe here, or the store actually happening to memory, until later. And what it allows you to do is you can basically have commit in order. You can pull back these things earlier. This looks like a typo. This should probably be back 1. And then you can commit in order and have that store sort of still outstanding out to main memory. One important thing you need to do here is, as I have said before, if you let another load into the pipe or a store into the pipe, you're going to have to bypass out of this data structure and that data structure now back to the load stage of the pipe or the store stage of the pipe. And that adds extra wires into your out-of-order processor. But we've basically decoupled store committal from, or it's technically committed once it gets past this point, but it's not in main memory. But it's to everyone else and to the processor, it looks like it's been committed, because you try to go read the value and it looks like it's committed.